Before we can dive into the project itself, we need to understand the experiment. Originally, we have an autonomous robot predator that chases after a mouse. It moves towards non-visible locations until it sees the mouse. After it spots the mouse, it will begin chasing after it. At any point, if it loses sight of the mouse, it will go to the last known location. The purpose of these experiments are to understand planning within mammals. We elicit this behavior in mice by having them evade a predator in the form of a robot that emits compressed air when the mice gets too close. One of the problems with the current experiment is that the autonomous robot is purely reactive. When we have a mouse that can outrun the robot itself needs to start planning in order to better simulate a predator. This is the purpose behind my project, to use a real-time planning agent to control the robot. And what better planning agent than a human? Here's what the robot looks like. It's a skid-steer robot that has two sets of wheels that drive a pair of treads. There are two PCBs on the robot, one with an ESP32 microcontroller that controls the wheel speed commands, and another PCB that controls three LEDs that are used to track the location of the robot. It does this using a camera system up above the robot. The robot receives instructions on where to move from a nearby server, which also holds the tracking information. These are converted into wheel commands the robot can follow. The original habitat is a 2-meter hexagonal world which has a mouse with an average body length of 8 centimeters. It features hexagonal occlusions or obstacles that occlude the view of both the predator and the prey. Now, we can't feasibly build a world proportional to the habitat for a human player. This is why we chose to create a virtual reality environment. Now, one of the biggest challenges with that, however, is allowing the player to be completely untethered. We have a battery-powered VR backpack that the players can wear and run around in, and a VR headset that accompanies it. We combine these two together with a step-up module that are designed which allows the VR backpack to power the VR headset, letting the player be completely untethered. The reason I had to design the step-up module is because there currently isn't a proprietary cable that connects these two components together. In order to translate coordinates from the VR world to the habitat, I needed to define an equation that would convert the two. First, we have what's called the canonical coordinates, denoted with a C. This is the current VR coordinates plus half the length of the virtual map divided by the full length. Second, we have the virtual coordinates, which are the canonical coordinates multiplied by the length of the map plus or minus half the length of the map. At the end, we get a smooth transition between the two worlds. To communicate between the game and the server, we have a client-server relationship. As the player walks around in the virtual environment, their movements are matched by the robot. The tracking server then updates the location of the ghost, which represents the real robot's location inside the game. This is to help understand where the player is in relation to the real robot. Tracking information of the mice is also sent to the game and updates the mouse avatar. This networking feedback loop is what allows the player to have a real-time experience with the mouse while running around in a field. With this new system, we are looking to make new discoveries in the planning world. Inferences from these studies can lead to finding more efficient computer algorithms. Getting a better understanding of planning within the brain can also shed light on mental health disorders, like schizophrenia, anxiety, and addiction, which are all associated with planning and habitual activity-related circuitry. In the future, we hope to better localize the player by adding in a mini-map for the location of the robot and the location of the mouse when it's spotted. Furthermore, we can incentivize the human to stay close to the robot by creating a dimly lit world that is hard to navigate. In order to counteract the darkness, the ghost, the representation of the robot, will emit light, which in turn forces the player to move at the pace of the robot. Thank you to everyone who helped out with this project, and thank you for watching. It's taken another surfing ride.
Oh my gosh, really?
Yeah.
Oh wow. So cool. I'm being ridden.